Hello and welcome to today's lesson looking at atmospheric pressure. So we're going to try to apply our understanding of atmospheric pressure and fluid pressure to different situations. Now this particular lesson links into the AQA GCSE Physics in the Separate Science course in the Forces module, which is found in paper 2. So in today's lesson, what we're going to do is we're going to try and define what fluid pressure is, calculate fluid pressure, and then detail and describe the properties of atmospheric pressure, which links into the following part of the AQA GCSE specification. So it links into the pressure in the fluid part of the course which you looked at in the previous lesson, and into this particular part which we looked at the previous lesson, but then it also links into this particular part of the AQA Separate Science specification for physics, which is atmospheric pressure, which looks at what the atmosphere is, how atmospheric pressure is created, and how atmospheric pressure varies with height. Now, like the material for fluid pressure, atmospheric pressure is separate science only content, which means that if you do AQA GCSE Combined Science, you will not be assessed on your understanding of fluid pressure or atmospheric pressure. Now, in the previous lesson, we looked at the pressure at the depths of liquids, but how does pressure change in the gases of the atmosphere? Well, like mentioned before, the atmosphere of the Earth is an absolutely amazing aspect of the planet. The atmosphere is a mixture of predominantly nitrogen, oxygen, and other gases such as carbon dioxide. Now, the first atmosphere of the Earth was mostly carbon dioxide and methane, which were emitted from the first volcanoes of the Earth, but over time, plants which photosynthesized removed that carbon dioxide and replaced it with oxygen, so the amount of carbon dioxide went down and the amount of oxygen went up, and nitrogen was also released in different reactions, which eventually allowed for animal life to develop on the planet. Now, the atmosphere is also very, very useful because it protects living organisms on the Earth from the sun's harmful ionizing radiation, which is the high frequency part of the electromagnetic spectrum, which includes ultraviolet, X-ray, and gamma radiation. Now, organisms can either have skin cancer or general cancer from these types of electromagnetic radiation. Now, predominantly, the part of the atmosphere which will absorb these parts of the radiation and will not allow them to hit the surface is the ozone layer. Now, the atmosphere, whilst on the human scale is large in comparison to the Earth, it's in fact tiny. We believe the atmosphere is only about 100 kilometers in height from the surface of the Earth. Now, compared to the size of the Earth, that's absolutely minuscule. If the Earth was the size of a basketball, the thickness of the atmosphere could be modelled by placing a thin sheet of plastic or laminate around the ball. So it's like putting a varnish on a football. Now, the atmosphere exerts an atmospheric pressure. Now, at sea level, we measure this pressure of the atmosphere as 1 atmosphere, or around about 101,000 pascals. But how does air, which is a mixture of gases of oxygen, nitrogen, carbon dioxide, methane, how does it produce a pressure? Well, if you live in the atmosphere of the Earth, you're constantly surrounded by the particles of the air. Now, these gas particles will move about in random directions with a variety of speed. Now, we know air, because it's a gas, is a fluid, because it can flow, since the particles are able to move around. Now, in this motion, some of the particles will collide with the objects present in it. So, if you put a box in the air particles will collide with the surface of the box. Now, this will exert a force on this particular object, and because pressure equals force over area, this will then produce a pressure. So as a result, this pressure means that the force is exerted in normal or right angles to any surface which the particles hit. So whilst they seem like different effects, fluid pressure in the liquid form and fluid pressure in the gas form are actually the same effect. So the pressure that is produced in the ocean and the pressure that's produced in the atmosphere is actually the same effect, just manifested in different ways for us humans. Now, as well as that, we experience different values of these pressures because we live in different parts of these particular bodies of fluids. So because we live at the top of the ocean, all of the ocean is below us, now we actually experience quite a low pressure in fluids at this top. However, because we live at the bottom of the atmosphere, all of the atmosphere is above us, we actually experience a high atmospheric pressure compared to if you travel further upwards. So we live in a region of low liquid pressure but high gas pressure due to our position on the Earth. And actually we can consider both the atmosphere and the ocean to be oceans themselves, and like Torricelli once said, a very famous Italian scientist, we live submerged at the bottom of an ocean of air. Now, we looked at this previous demonstration indicating how pressure can change with depth in a liquid. So in an open system for a fluid, okay, the pressure increases with depth. So because we're at the top of the ocean, we experience a low pressure, but at the bottom of the ocean, if we went to the seabed, we'd experience a high pressure. But in terms of the atmosphere, because we live at the bottom of the atmosphere, we experience a high atmospheric pressure, but if we went higher and higher and higher up in the atmosphere, we'd experience a lower and lower and lower atmospheric pressure. Now, atmospheric pressure works in the same way as fluid pressure, okay, in terms of a liquid. Now, there's actually a couple of important ideas you've got to understand. That when you are close to the surface of the Earth, when you are not very high up in the atmosphere, when you are at a low altitude, you have a high atmospheric pressure. But the higher up you go in the atmosphere, the lower the atmospheric pressure becomes. So atmospheric pressure will decrease with altitude, it will decrease with height. Now there are actually two reasons as to why this is, because fundamentally the higher up you go in the atmosphere, there is less weight pushing downwards exerting the pressure, and there's two different reasons for this. Reason number one, there are fewer particles pushing down as you are higher up in the atmosphere, so there are fewer particles above this particular point. So the higher up you go, there are fewer particles going to be above you exerting a weight downwards, so therefore the force will be lower, so the pressure is lower. So there are fewer air molecules in total above the point you are measuring. But the second reason, which isn't common with the ocean, is that there are fewer particles pushing down as there are less particles the higher up you go, since the atmosphere becomes thinner with altitude. So you can also phrase it as the particles are further apart. The density of the atmosphere has decreased with altitude, so there are fewer air molecules per cubic meter. So there are two reasons why the pressure will change: the number of particles present and the amount of force acting downwards. Now we can actually work out the pressure at various parts of the atmosphere with the same equation we can for a liquid, because it's just a fluid. So pressure equals height times by density of the gas times by the strength of gravity. Now you are given this equation in your examination. It is found on the equation sheet at the end of your exam, but you are not given the units for all the values or the situation to use this in. So you need to know that you use this particular equation for a fluid in an open system such as the ocean or the atmosphere. Now it is my advice that actually you just memorize the equation anyway, because it allows you to use it quickly and easily in examinations. Now again, it's the same principle as the equation of pressure in a fluid, because it is literally the same concept. Now let's just clarify what we know, that although we measure the height from the surface when we calculate the atmospheric pressure, as it's more relevant to us, not depth, we can say that the atmospheric pressure will decrease with height or decrease with altitude. So when the distance from the surface of the Earth is high, the pressure is low. However, when the distance from the surface is low, the pressure will be high, and that's a very, very important idea. Now, what is the reason for this? There are fewer particles above producing a weight downwards, and the particles are further apart. There are fewer particles there to exert this weight downwards. So let's just recap what we've learned in today's lesson. Atmospheric pressure is created on a surface by air molecules colliding with the surface. That could be anything: a human being, it could be a table, it could be a box, it could be a mountain, it could be anything. Now, there are two reasons as to why the atmospheric pressure can change. Now, the greater the number of particles above a point in the atmosphere, the greater the weight acting down and producing a force. Okay, so the greater the pressure, and secondly, there are fewer particles higher in the atmosphere producing pressure as they are further apart from each other. Now, this leads to one key concept. These two reasons lead to one key concept. As the height increases, the atmospheric pressure decreases. So the higher up you go in the atmosphere, the higher up you go from the surface of the Earth, the lower the atmospheric pressure becomes. So let's just summarize what we know about pressure in fluids for this particular part of the course. A fluid can either be a liquid or a gas because the particles can flow, they can move. Now, the pressure in fluids causes a force normal at right angles to any surface, and the pressure at the surface of a fluid can be calculated with the equation P equals F over A. Now, that is an equation you've got to memorize for your examination. You've got to learn it. Now, the pressure due to a column of liquid can be calculated with the equation pressure equals height of the column times by the density of the liquid or the gas times by the gravitational field strength. Now, please also note that both of the equations, this one, which you are given in the exam, and the previous one, which you're going to memorize for the exam, can calculate pressure in a fluid. So if you're doing a question about a liquid or a gas, you can equate the two equations to each other because they're both calculating the same pressure. Now, you should also be able to calculate differences in pressures at different depths in a liquid, and that you understand that a submerged object experiences a greater pressure at the bottom of its surface than on its top surface. So there's an imbalance in the pressure, and the only thing that causes a change in pressure is a resultant force. So that change in pressure produces a resultant force upwards, and we call that force upthrust, which links into how objects will float and sink. And then finally, the atmosphere is a thin layer relative to the size of the Earth in total of air around the Earth, and the atmosphere gets less dense with increasing altitude. Now, when air molecules collide with the surface, it creates atmospheric pressure, and the number of air molecules, and so the weight of air above a surface, decreases as the height of the surface above the ground level increases. So as height increases, there's always less air above a surface than there is at a lower height. So atmospheric pressure decreases with an increase in height. And you should also be able to describe a simple model of the Earth's atmosphere and what atmospheric pressure is, and explain why atmospheric pressure varies with height above a surface. I hope you've enjoyed today's lesson, where we can define what fluid pressure is, calculate what fluid pressure is, understand how the atmospheric pressure can change, and detail the properties of atmospheric pressure in a high-level concept. Now, hopefully you've enjoyed today's lesson, and in future lessons we'll be looking at motion and we'll be looking at Newton's laws of motion. I hope you have a lovely day and take care.